This section looks at the basic principles of carburetted systems. A basic carburetted system consists of the fuel tank to store the fuel. Fuel lines or pipes carry fuel in the system. A pump moves fuel from the tank to the engine. A filter cleans the fuel. An air cleaner supplies clean air. A carburetor mixes the air and fuel and controls how much mixture enters the engine. An intake manifold carries the mixture to the engine. The carburetor has to supply the correct mixture of air and fuel to suit all operating conditions. The downdraft carburetor is the most common kind. It's mounted on the intake manifold. The side draft model is less common. The carburetor turns liquid fuel into a fine spray and mixes it with air. It also controls how much air-fuel mixture is delivered to the engine. This is done by the throttle valve near the bottom of the carburetor, which is connected to the accelerator pedal. This downdraft carburetor has a float bowl for fuel. One end of a tube is immersed in the fuel. The other end is a fuel discharge nozzle in the venturi. As the piston moves through intake, it makes a low pressure area, and as a result, air from the atmosphere flows through the venturi. The venturi here is narrower than the rest of the barrel, and it is shaped to make the air speed up as it passes through. A similar effect occurs around the wings of aircraft. The shape of the wing section speeds up the airflow over the top of the wing and creates a low pressure area there, lower than the atmospheric pressure below. The result is an upward force that provides lift for the aircraft. The shape of the venturi is designed to apply the same principle. It creates a low pressure area where the end of the nozzle protrudes into the airflow. Atmospheric pressure on fuel in the float bowl is now greater than the pressure on the end of the nozzle. This forces fuel to flow from the nozzle. It mixes with the passing air, breaking up into droplets or atomizing. A light vehicle under normal conditions needs an air-fuel ratio by mass of about 15 to 1. By volume, that's 11,000 to 1. This ratio can vary to suit engine operating conditions. Too much fuel for the air will waste fuel and cause pollution. Too little will cause loss of power and possible engine damage. The carburetor supplies the engine with the correct mixture to suit all operating conditions, from idling to high speed. To do this, it has a number of systems. With the engine stopped, the throttle valve is closed, but fuel is still held in the bowl. With the engine running, fuel is held at a set level by the float and a needle valve. Fuel supplied to the engine when it is running is replaced by fuel from the tank. A passage from the air horn to the float bowl balances air pressure between the air cleaner and the float bowl. The idle air passage and the main discharge nozzle are above the level of the fuel. The first stage of the idle system uses the idle and low speed circuit, plus an idle adjustment screw. The throttle valve is almost closed, so airflow through the carburetor is very small. The action of the piston creates a low pressure area below the throttle, and this is concentrated at the edge of the throttle valve as the air passes the idle port. Fuel flows from the float bowl through the idle passages and into the carburetor below the throttle valve at the idle port. The air bleed lets air enter the fuel on its way from the float bowl. This helps aerate the fuel before it reaches the idle port. Engine idle speed is set by two different adjustments. The amount of fuel is adjusted by the mixture adjustment screw at the idle port. The amount of air is adjusted by changing the throttle stop screw. Second stage idling starts as the throttle valve opens. This is similar to idle, but with the low speed port uncovered. Both ports discharge fuel to mix with incoming air. Low speed ports help the transition from idling to low speed to high speed. Without them, the engine tends to hesitate until the main system comes fully into action. The main or high-speed system comes into action above fast idle as airflow through the venturi increases. A main metering jet in the fuel in the bowl meters fuel passing into the discharge nozzle. How much fuel leaves the nozzle depends on the pressure difference created by the airflow through the venturi. As the throttle opens and airflow increases and speeds up, more and more fuel is drawn from the discharge nozzle. However, the mass of air doesn't increase in proportion with the speed, and as a result, high speeds can produce a mixture that is too rich. To correct this, more air can be added. This is called compensation by air correction. As the throttle opens and engine speed increases, the level in the jet well falls, exposing air bleed holes in the discharge tube. Air can now mix with the fuel and stop the mixture becoming too rich. As the throttle opens further, the fuel level falls too, exposing more air holes. More air bleeds in to maintain the correct mixture. The size of the main jet is selected to provide the best mixture for economy under cruising conditions. When the throttle is opened wide for maximum power, a richer mixture is required. The extra fuel is provided by a powered jet with a vacuum piston and rod opening it as it is needed. At low speeds, intake manifold vacuum is transferred through a passage to the vacuum piston. This holds the piston up and keeps the power valve closed. With the throttle valve fully open for full engine power, the vacuum in the intake manifold falls. A spring pushes down the vacuum piston and rod to open the power valve. Fuel flows through a bypass jet to enter the fuel well and add to the fuel from the main jet. This provides the extra fuel needed to enrich the mixture for full power. Extra fuel is also needed for accelerating. Suddenly opening the throttle increases the airflow, but fuel cannot flow from the discharge nozzle quickly enough to match it. An extra jet of fuel is needed. Depressing the pedal compresses a duration spring that exerts a force on the plunger of a small plunger pump. This pressurizes fuel below the plunger and closes off the inlet valve. Fuel flows through a bypass jet and enters the airstream from a discharge nozzle above the venturi. The duration spring extends the time for delivering the fuel. Releasing the pedal lets the linkage move the plunger upwards. The bypass jet closes and the inlet valve opens to let fuel refill the pump chamber from the float bowl. When a cold engine is being started, little air flows through the venturi, and there is no heat to assist in vaporizing any fuel that is delivered. This makes the effective mixture of fuel and air too weak to be readily ignited by the spark plug. An excess of fuel must be supplied temporarily to ensure that the proportion of fuel that does vaporize will form an ignitable mixture. A choke valve is fitted to help. Closing the choke valve closes the carburetor intake. The pumping action of the pistons creates a low pressure area below the valve even without venturi action. This low pressure causes fuel to flow from the discharge nozzle and from the idle and low speed ports and provides the rich mixture needed to start the cold engine. The choke can be controlled manually by a cable that operates the valve. Most are controlled automatically, so that the valve is closed when the engine is cold and opens progressively as the engine warms up. When the engine is warm, the fuel drawn into the manifold during starting vaporizes readily, and the engine can be started without the aid of a choke. The choke should operate as briefly as possible. Overusing it produces rich mixtures that cause exhaust pollution and increase fuel consumption. Flooding a carburetor also produces rich mixtures. This can be caused by wear or by dirt trapped in the needle and seat that causes the level in the float bowl to rise and fuel to discharge from the nozzle, with little or no venturi action. Carburetors can have a single barrel or 2 or 4 barrels. Extra barrels improve performance, particularly at high speeds, letting more air enter the cylinders than with a single barrel. Two barrel carburetors have two outlets to the inlet manifold and have two basic designs. One has a common float chamber, but each barrel has a complete set of all other circuits, and the throttles can open simultaneously. The float chamber may be straddled by two connected floats that almost surround the air passage. This leaves it unaffected by cornering, climbing, accelerating, or braking. The other basic design has throttles that open in two stages. It combines the two barrels to act as a single carburetor. The two stages combine good low-speed operation of a single barrel design with the extra airflow of two barrels. One half of the carburetor has all the circuits needed to supply mixtures for the whole range of operation. This is called the primary side. The other barrel, the secondary side, supplies extra mixture but only at high speed or full throttle. It normally has a main metering system and a non-adjustable idling system. The primary side has a choke for cold starting. When the engine is being started, the throttle on the secondary side is already closed, so a choke isn't needed. From idle to medium speeds, only the primary throttle is open. When engine speed rises to where additional breathing capacity is needed, the secondary throttle opens to admit more air-fuel mixture. By the time the primary throttle is wide open, so is the secondary throttle. This can be controlled mechanically or by a vacuum unit connected by pull rod to a lever on the secondary shaft. When air flows past ports in the venturis, it produces low pressure areas. A hose transmits this low pressure to a diaphragm chamber. This low pressure acts on the diaphragm and opens the secondary throttle. Large capacity V8 engines may use a 4-barrel carburetor of two-stage design, effectively two two-stage carburetors combined, with each side supplying 4 of the 8 cylinders. A central moulded plastic fuel bowl and suspended metering system can be incorporated into the design. This gives lower fuel temperatures with more precise fuel metering and closer control over air-fuel ratios.